Hello class. So we've been working on quadratic functions, drawing parabola based on vertex form, standard form, factor form, and from each of those forms we were able to identify a few things. Starting with the vertex form, you can identify the vertex, and if you're talking about standard form, you can identify the y-intercept, and if you're talking about quadratic function in factor form, you would then be able to identify the zeros or the x-intercept based on the numbers given here and there. So each of these forms give us some advantages. But I'm pretty sure as we've been working on quadratic functions, you would agree with me that a quadratic function in vertex form will give us the most information based on the availability of the vertex, P and Q. Every time when you are to draw a parabola, once you have the vertex, once you know the location of your vertex, you can then create your parabola based on the size given to us, and of course the direction of opening. So what we are going to do is to look at some quadratic function in different form, in particular in standard form, and we want to come up with a way to convert a quadratic function in standard form back into vertex form. So this method is what we call completing the square. We are going to use the three terms in your standard form and see how these three terms will create the perfect square that appear in vertex form. That's what it means by completing the square that you see in this equation. But before we do that, I'm going to walk through some of the basic concepts that you need to know in order to complete your square. So I'm going to look at example number 1, where it consists of two perfect squares, whether it is x plus 3 square or k minus 7 square. As you are to expand the perfect square, some of the move that you need to do is to multiply the same two terms twice. You can expand it by using FOIL, or some of you probably will have a better skills by simply expanding your expressions using a formula here. But let's just assume that everyone needs some kind of review, and we are just going to expand this perfect square by FOIL. So what you would do is to multiply this by that for the first, and then outside, so that will give us 3 times x, or x times 3, and then for the inside 3 times x, and finally the last terms of the two brackets. So in this case, as you simplify the expressions, we have x squared at the beginning, we have 3 squared at the end, and what happens is the two middle terms are the same. So you're basically adding 3x 2 times. And therefore, as you expand your perfect square, you will end up with a trinomial, starting with a perfect square, finishing with a perfect square. 9 is a perfect square. And then at the end, the 3x in the middle, as you are adding those two terms twice, you end up getting 6x in the middle. Now using the same concept, if I'm to expand k minus 7 square, if I'm to expand this perfect square, I would multiply this by that using FOIL. And as I multiply it, I end up getting k squared, k times 7 with a minus, and then for the inside we have minus 7 and times it by k, that gives us minus 7k, and finally negative 7 times negative 7, that will give us 49. So similar to the previous case, we're still going to come up with a perfect square at the front and at the end. And these two terms, the front term and the end of term, these two perfect squares are actually from the question here, the k and the 7. And those two middle terms here, given we are to subtract 7k twice, you will end up getting 14k, minus 14k in the middle. So here comes a pattern as you expand a perfect square. You will always end up with a perfect square at the front, a perfect square at the end, and these two terms are perfect square of k and 7. Or in this case, in the previous case, the x square and the 9, these two terms are the perfect square of x square, you just end up with x square. And the 3 here, 3 square, give us the 9 here. The middle term that you see will always be twice as much of the number here or there. If you are working with 7, we end up with 14. If the perfect square comes with a 3 here, we end up getting a 6. So in order to go backward and do the reverse, I can start with this middle term, and knowing how this middle term is twice as much of what you would see in this bracket, I can then come up with the number that will give us the perfect square inside the bracket, or that means the number that will create this perfect square at the end. So whenever you work with a trinomial, starting with this middle term, let's say in this example 6, I can divide it by 2, and this will be the number that we are using for the perfect square. So I'm going to go over example number 2 to give you some more detail.